Hey, discrete math students. Welcome to this extra example video on proving existentially quantified statements. I'm going to go a little nuts this time and try to do two examples on this, or three examples actually on this one video. A little ambitious perhaps, but I love to do lots of examples of this, and I think it's really great for you to be able to see more than just a few we were able to do in class. So let's take a look here at our first example. So in this example, it has to do with baseball. A baseball player has won the Triple Crown for batters in the American League since 1950. This you can see probably that it's existentially quantified. The word has here is a bit of a tip off to that, but it is claiming that there's a certain element that exists, and it would be the element of, you could say, a set of baseball players or professional baseball players in the American League, something like that. We're saying that there's an element that exists in that set. So now, you may not know anything about baseball, and you may wonder, well, how in the world am I going to prove this or come up with an example when I'm not even sure what it's talking about? Okay, well, when you're in a situation like that, which is actually not too unusual when you're trying to do a proof, the situation of not really fully knowing what's going on there, one thing that can help is just to really see what kind of statement you're dealing with, what you're going to need to do. You can rewrite the statement in standard form. And it's not really in standard form quite as is, so let's see if we can get a little closer. So I'm going to say there exists. It's existentially quantified. We know it's going to start like that. And again, what the set is here will be the set of baseball players, let's say. There exists a baseball player. We don't have a symbol for that, so we'll leave it in words. Okay. This is Cleo, by the way, one of our cats. Okay, there exists a baseball player, and we need to say what the properties are, what the conditions are in this baseball player, who was playing in the American League, one of the two major leagues for baseball in the United States. So playing in the American League. And this also has to have occurred since 1950. And then the other condition is winning the batting Triple Crown. Let's see. Let's good. I left plenty of space there. And won the batting Triple Crown. Okay, so now you could say, a little bit clearer the structure of the statement and what kind of tactic we're going to need to take to prove this. We need to come up with an example and so forth. And we see the conditions that need to be met. But you still may be left wondering, well, what does it mean to win the Triple Crown? So a second practice that is often very helpful, and these are besides experimenting. We've talked about experimenting in class. Another helpful tool in preparing and planning out that proof is to take a look at the definitions of the terms in the statement and think about how can I use those definitions perhaps in constructing my proof. Now, of course, you may come across definitions that you don't know what they mean. And so sometimes when you're trying to figure out how to do a proof, some research is going to be involved. So one thing you might need to research is, what do the words in this statement mean? You got to have a good understanding of that if you're going to be able to prove the statement. Yeah, so again, no shame in that at all. As the great mathematical expositor Bud Brown said, research is what you do when you don't know what you're doing. So that's probably what we need to do here. You could go take a look at, let's see if I can find here. Okay, get in my somewhere here. A lot of things. My Google. Oh, wow. Oh, there it is. Yeah. Go in here, look and see what Triple Crown is, and so forth. And, oh yeah, Triple Crown leads the league in 3 categories. Okay, and then we can go from there to back to working on our proof more directly. Let's see. All right, so here's our definition that we'll use in baseball. A batter who leads the league in batting average, home runs, and runs batted in for a season is said to win the Triple Crown for that season. There is a sort of a pitching Triple Crown, less well known, but just to clarify, we looked at the batting one here, and it turns out this is a pretty rare thing to do. And so now some additional research that would be involved is probably looking at some stats, going back and seeing when you can find a situation where there was one player who led the American League in all 3 of those categories. That kind of research is a lot easier than it was in days of old, as long as you can find online sources that you're willing to trust. Okay, so back when I started teaching this course, you had to go back a long way to find someone who did this. But then Miguel Cabrera came along. It turns out that he provides an example. And again, you can find that pretty easily with some looking up of the statistics. There's our definition again. Keep that first and at front and center here as we look at making sure that that definition is verified. So I'm going to start my proof of this existentially quantified statement by giving my example. Miguel Cabrera. Okay, and he is such a player, so there's my example. And now I need to verify that Miguel Cabrera satisfies the conditions. So, in 2012, okay, that's a year since 1950. We could emphasize that. I'm going to say that goes without saying. But I am going to mention that he was playing for the Detroit Tigers. And the relevance of that is that that's an American League team. Another one of our conditions is satisfied. Okay, now he won the Triple Crown, so I'm going to mention specifics here. He had 330 batting average. Seems like a small number if you're not familiar with baseball, but that's actually really good. 44 home runs. Pretty impressive as well. And 139 RBI. Leading the league in each category. And since he led the league in all 3 of those categories, he won the Triple Crown. All right, now you may wonder, I'm going to say, we've satisfied the conditions. We'll end our proof there, maybe, with a little square. You might wonder, why provide the details here, like the batting average and the number of home runs and the number of RBIs. You could say, well, really the argument still stands without those. But what those specifics do, giving the specific year, the specific team, and all these things, they lend more credence to the argument. They make it more convincing. Details can do that. And that is the flip side of the proof coin. On the one hand, our proofs need to be structured correctly. They need to be logically sound. Mathematically, everything has to be correct. That's an essential side of a proof. But the other side of a proof is that it is an argument meant to convince somebody that your assertion is true. And so there's sort of a psychological aspect to it as well. We don't want to neglect that. We want to make sure that we're doing all that we can to make sure our reasoning is convincing as well as correct. Okay, so that's the first example. Let's go to something more mathematical now. There exists a rational number x such that, extra and in there, such that 5 is less than x is less than 6. As we know, 5 less than x less than 6, that's actually a conjunction. There are two inequalities there, which are both being required to be true. Okay, so first we need to come up with our example here. And there are actually a lot of numbers you could choose, but almost everybody tends to go for the most obvious one, which is 11/2, which you might also do as 5.5. That'd be okay as well. You just have a little bit of different flavor in your proof if you do it that way, but it's the same number, and so at the end of the day, it comes out the same way. This is just the average of those two numbers, so it certainly seems like it should be in between, but again, we want to provide some justification for that. Okay, well, one thing we can presume is the ordering of integers, and so I'm going to do that with 10, 11, and 12. And that's something that is a permissible assumption. So the ordering 10 less than 11 less than 12 of integers is well known. Okay, and now we can divide by 2. And the key thing here is that 2 is a positive number. So dividing by the positive number 2, well, okay, I'm going to mention it preserves the inequalities. Again, that's always something you got to be cognizant of when you got inequalities, that whatever you're doing is going to preserve them. So it preserves the inequalities, which again there are 2 of really. And that's going to give 10 over 2 less than 11 over 2 less than 12 over 2. And of course that we can rewrite, not using an equal sign of course, but a thing that I like to use here is i.e. That is, you could write it out as well. 10 divided by 2 is 5. 11 divided by 2, that's our x. 12 divided by 2 is 6. So x is indeed between 5 and 6. There is one other detail here that we got to make sure to check, and that's that our chosen example is in the domain. Again, you might say, well, that's obvious, but let's go ahead and confirm it and justify it with something to make our argument airtight and fully convincing. So as a ratio of 2 integers, and it's a ratio of 11 and 2, we can presume that those are indeed integers with non-zero denominator, because 2 is non-zero. Very long word. Okay, this gives us that x is a rational number. Okay, and so x satisfies all the conditions. We'll just say that. And our example is verified. And so we're done with proof number 2. All right. Well, let's go on to one more. One that's perhaps not quite as obvious. Okay, what are we going to do in a situation like that? Okay, here we have, again, a clearly existentially quantified statement. There exists an integer n greater than 20 whose proper divisors have sum exactly n. Okay, so here again, you may or may not be familiar with what a proper divisor is. If not, a little bit of research goes a long way. A proper divisor of a positive integer n is any positive divisor of n other than n itself. Okay, so we cannot use the number itself as a divisor, but any other divisor will be okay. And at some point, you presume that you know what's going on here, that you know what a divisor is. Now, that said, you may know all day long what divisors are, but can you find a number that does this? You add up the proper divisors of it, and you get exactly that number. Well, it's perhaps not at all clear what a number like that is going to be. And this is where, again, experimenting as part of your process in planning the proof is a great tool, perhaps the best tool that you've got, or nearly the best, maybe. So what we can do here is we can try out some different values for n and just see what happens. Okay, 21, that's greater than 20. Certainly, well, most likely it wouldn't be worthwhile trying anything below 20 unless we were just trying to get some kind of, get our foot in the door or something with this, with some smaller numbers. And then we want to look at the sum of the proper divisors and see what we get. So for 21, proper divisors are 1, 3, 7. Now remember, we don't do 21 as a proper divisor, so those add up to 11. That's too small. Okay, that's less than 21, so that one's not going to work. So we go to 22, and its proper divisors are 1, 2, and 11. And there too, well, that's equal 14. That's also going to be too small, so it's less than 22. 23, it's prime, and its only proper divisor is 1. So I think from here, so you might wonder, my goodness, am I going to have to try every positive integer here? No, I mean, if you do enough of this, you develop a sense for, what kind of things are definitely not going to work, what kind of things are likely to be closer. I don't know if we're going to get to that point here. But one thing I think we can say now right away is, if you got a prime number, it is not going to work for this, because a prime number, its only proper divisor is 1. It's never going to add up to be the number that you started with. Okay, so, but with that knowledge under our belts, let's keep going to 24. Oh, it's got a lot of proper divisors. 1, 2, 3, 4, 6, 8, and 12. And if you add all those up, you might think, wow, this is pretty promising. But if you add them all up, it's actually 36. And nuts. That's too big, because we want it to add up to exactly 24. Maybe it's a little encouraging because we see that the sums can get big enough. We just have to find one that gets exactly right. 25, its only proper divisors are 1 and 5. Too small. 26. We got 1, we got 2, we got 13. That's it. That's up to 16. Nope. 27. We got 1, 3, and 9 as the proper divisors. And those add up to 13. Nope, too small again. Uh-oh, I'm running out of space. Let me go over here. 28. Okay, now it's divisible by 1 and 2. It's also divisible by 4. 4 times 7 is 28, so 7 is the divisor, and then we got 14 that pairs with a 2, and that's it. And if we add these up, it comes out to be 28. Bingo. Experimentation complete. In this case, as soon as we come up with an example, we can stop, and we can go ahead and write the proof. Let's see. I don't think did I put proof here? Probably not, so I'm just going to write it here. Let's, first of all, let's make a clear division. Make a really thick line here, which should go including that. Okay, because what we did over here, this is our analysis. Okay, experimentation, writing out definitions, things like that. Those are analysis of the planning process of the proof. We want to make a clear distinction between the analysis and the proof, always. Okay, so now we can write the proof. Okay, so I can say consider the integer n equals 28. I'll mention, because that's one of my conditions, that it is greater than 20. Okay, that one's easy enough to believe, and so we don't have to say anything else about that, although perhaps I should make my 2 a little better. Okay, it's greater than 20, and then we just need to show that it satisfies this condition about the proper divisors. So I'm going to say the proper divisors of n, or you could say 28, are 1, 2, 4, 7, and 14. Their sum is 1 plus 2 plus 4 plus 7 plus 14 equals 28, which is n. Okay? And so the sum of the proper divisors of 28 equals 28. I mean, we're basically done. I'm just going to say, hence, n equals 28 is an integer greater than 20. Maybe I won't put that again. Whose proper divisors add to itself, let's say. And we'll say add to n. Okay. That should be a good enough conclusion, I think. And so that brings us to the end of extra example 3 on proving existentially quantified statements. Okay, I feel a lot better now that you've seen a good number of examples of proving existentially quantified statements. And I think you can expect something on universally quantified statements sometime soon, hopefully. And we'll see you before long.